are currently discussing multiple regression. In our previous class, we have started our discussion on multiple regression. A quick recap of the things. So, if we take a simple model wherein there is only one explanatory variable, like the one that quantity demanded is a function of price, then we are ignoring many things, like if we are discussing the demand for tea, then we are ignoring things like the price of substitute, that is coffee, the monthly income, the wealth, and the wealth condition of that person, and the taste and preferences and things like this. So we need to incorporate many of these. If we need to incorporate these items, we have to move from bivariate to multivariate regression. Here, all these things we are clubbing it under the ceteris paribus, and these things are sitting in our error term. But since there is never an exact relationship between variables, how do we allow for these other factors which are affecting y? Through multiple regression. Again, what is the functional relationship between x and y? Is it linear or non-linear? If it is non-linear, we have to incorporate a quadratic term. When we are incorporating a quadratic term or any other a cubic term, so we are moving from the realm of simple regression to multiple regression. Again, how can we be sure that we are capturing this ceteris paribus? We are capturing this set. How can we be sure that we are capturing this ceteris paribus relationship? So, when these things are involved, when we need to incorporate more than one independent variables, we come under multiple regression. Here the assumptions, they are almost the same like the one which we had when we discussed our classical linear regression model. In the bivariate case, that the error term is random, the error term has zero mean, error term is same for all the values of x, the error is normally distributed, the error is not correlated, the errors are independent of the explanatory variable, there are no errors in measurement, there is correct aggregation of the variables, the relationship is identified, the model is specified, and along with it, there is another important assumption that there is no problem of multicollinearity, meaning thereby there is no perfect relationship between the different independent variables. If the different independent variables are perfectly related, then they will be falling to the problem of multicollinearity, where it can be a case that we are not even getting the estimates. So the assumptions are the same as such. Then we moved on to the derivation of beta 1 hat, beta 2 hat, or as many betas are possible over there, as many independent variables are there. So for that, we started with this regression equation: beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 along with I. Then what is error? Error is actual y minus y hat. This, if we do the summation and square and summation, we get this equation. That is summation under bracket yi minus beta naught hat minus beta 1 hat minus x1 minus beta 2 x2i and whole square. Now this equation is used to derive these three normal equations. We differentiate this equation with respect to, we do the partial differentiation of this equation with respect to beta naught and then beta 1 and then beta 2. Upon doing this, we will get these three equations. We have seen in detail in our previous class. Then we have seen the value of beta hat, beta naught hat, that is the intercept term, and the value of beta 1 hat, and this is the value of beta 2 hat. Let us take one example of beta 1 hat is summation x1 yi multiplied by summation x2 square minus summation x2 y minus summation x1 i2 x2 i divided by summation x1 square summation x2 square minus summation x1 x2 the whole square. Similarly is the formula for beta hat. Then we have also seen another method where we are not using where we are using the deviations, that is we are using small y hat, which is nothing but capital Y hat minus y bar, and so my y hat is this equation, my y bar we divide by n. We simply divide it by n, we get this y bar. So once we do y hat minus y bar, we come up with this equation with this beta naught cancels, and this is x1 minus x1 bar, this is equal to small x1, and x2 minus x2 bar, we get small x2i. Then we get e is nothing but small y, that is the actual small y minus estimated small y. So we put the value of y hat this over here, and then finally what we do the square and the summation of it. So we get this equation, that is summation yi minus beta hat xi minus beta 2 hat x2i the whole square of it. This this equation we again do the partial differentiation. Upon doing that, we get these two equations. These two are similar to the normal equations which we have derived in our earlier case, and from this also we can get the same values of beta 1 and beta 2. So these things we have covered in our previous class. Current lecture starts with the coefficient of multiple determination. See, when the variables are, when there are multiple explanatory variables, we refer to as multiple correlation. And the square of the correlation coefficient is known as the coefficient of multiple determination or square multiple correlation coefficient, denoted by the letter r square. And there are subscripts along with it. Along with r square, we write the subscript. For instance, in this case, that is where we have three variables y, x1 and x2. The squared multiple correlation coefficient is denoted by r square y dot x1 dot x2. And here the interpretation is the same like we had in our bivariate case, that in the two variable model, r square represented the proportion of the total variation of y explained with its relationship with x. Now here it is just changing that the variation in y that is explained by its relationship with x1 and x2. So this we can write it as small y hat square divided by summation small y hat square divided by summation y square. This is small y hat is nothing but y hat minus y bar, and y is nothing but y minus y bar. This can be written in this format also, 1 minus summation e square divided by summation y square, which can be also written in this format, where we take summation y square in the denominator on the full, and in the numerator it is summation y square minus summation e square. A derivation of it. So what we do, we take error e is equal to, all in the deviation format, yi minus y hat I. We multiply both sides by ei, so it becomes e square, and in place of then we write one of the e we open and other we keep it as it is. So summation yi minus ei is equal to this equation which we have derived earlier. So summation e square is nothing but the square of this. Summation e square is nothing but this particular equation, ei yi minus beta 1 hat ei x1 plus beta 2 hat ei x2, and by assumption this is equal to 0, this is equal to 0. So what we are left with, summation ei square is equal to summation ei yi. Now, once we have this summation ei, so if we square it, we can, in place of ei, we write this term, that is yi minus yi hat. Now we open this, we get this term, and then we multiply with summation yi. So summation ei can be written as summation yi square minus beta 1 hat summation yi x1 minus beta 2 hat summation yi x2. Now what we have done, we have just now defined this summation e square. So that is what we are taking the formula for r square in the case of multiple regression, and in place of e we are writing the complete term for e square. Now what we have, this we can write in this format, or we further simplify. Once we further simplify, what happens, this term, these two terms, they cancel out. This minus, it changes to plus. So finally r square can be defined as beta 1 hat summation yi x1i minus beta 2 hat summation yi x2i divided by summation yi square. Now the values of this r square, in case of multiple regression also, it will fall between 0 and 1. The higher the r square, the greater is the percentage of variation of x that is explained by the regression line, that is, better is the goodness of fit. And if the r square is closer to 0, the worse is the fit. But apart from r square, there is an additional concept of adjusted r square in the case of multiple regression. What happens that when we are adding a variable, we are also losing some certain degrees of freedom. It is important to note that including additional explanatory variables in the function never diminishes the coefficient. It diminishes the coefficient of multiple determination. It is important to note that, I am repeating, it is important to note that including additional explanatory variable in the function diminishes the coefficient of multiple determination. Sorry, I again repeat. It is important to note that including additional explanatory variable in the function never diminishes the coefficient of multiple determination. Instead, it typically increases it. See, r square is equal to summation y hat divided by y square, summation y square. By adding a new regressor, we enhance the numerator of the r squared expression, while the denominator remains constant. To address this issue, we adjust this r square by considering the degrees of freedom, which decrease as new regressors are introduced. In cases where n, that is the sample size, is large, both adjusted r square and r square would not differ significantly. But in smaller samples, if the number of x, the regressors, is considerable compared to the number of sampled observations, so the adjusted r square may be notably smaller than the r square. So basically r square does not take into account the loss of degrees of freedom, so we get the adjusted coefficient of multiple determination. The formula for this is equal to the first one, or it can be more simply written as the second one, that is 1 minus adjusted r square is equal to 1 minus summation e square divided by n minus k, the whole divided by summation y square divided by n minus 1, where n is the number of observations and k is the number of parameters to be estimated from the model, from the sample. Next, so a point to emphasize is, if we want to provide information that what percentage of relationship, what percentage of variance in the dependent variable is explained by its relationship with the independent variables, and if it is a case of multiple regression, that is there are more than one independent variables, then we should not report r square, rather we should report multiple r square or adjusted r square. It is called adjusted r square. Now we move on to the variance, mean variance of the parameters beta naught hat, beta 1 hat and beta 2 hat. Now we are not deriving the formulas over here, we are just writing the formulas for variance for beta naught, the formula for variance for beta 1 and the formula for variance for beta 2. We are assuming that there are only two independent variables. Now herein this expected value of beta hat is equal to of beta naught hat is equal to beta naught, expected value of beta 1 hat is equal to beta 1 and expected value of beta 2 hat is equal to beta 2. I repeat, here the expected value of beta naught hat is equal to beta naught, the expected value of beta 1 hat is equal to beta 1 and expected value of beta 2 hat is equal to beta 2. So the estimates of beta naught hat, beta 1 hat and beta 2 hat are unbiased estimates of the true parameters from the relationship between y, x1 and x2. That is, the mean expected value is the parameter itself. And here this because we are having this sigma square u, sigma square is equal to nothing but summation e square divided by n minus k, where k being the total number of parameters which are to be estimated. In our model it is 3. Now let us take a numerical example of our discussions on multiple regression. We take a data wherein quantity demanded is the dependent variable 8, 10, 20, 26, 36 and x1 is price, the first independent variable, and the second independent variable is income. So we are having two independent variables over here. Now let us we want to estimate the value of beta 1 hat. So the steps involved over here are is we have this data. First we do the summation of y, then divided by the number of items 5 we get y bar. We do the sum of x and we divide by the number of variables, we get x bar. Same thing for x2, that is income, we do summation x2 and then we get the mean of it. Then what we do, calculate small yi, which is nothing but yi minus, sorry, this is yi bar. There is only one I, so there is no need to be yi. So it is yi minus y bar. Y bar we have got 20, y is 8, 8 minus 20 minus 12, 10 minus 20 minus 10 and likewise. Then we do the same thing, this is small x 1i. So for calculating this small x, what we do, we for x1 we do 5 minus 13 we get minus 8, 7 minus 13 we get minus 6 and likewise. Similarly for the second variable, please note these corrections, these are small x1 and small x2 over here. There is a correction over here, there is also a correction over here. Summation small x2. So we have x2 I minus x2 bar. So the x2 bar is 144. So 10 minus 144, 133, 50 minus 144, minus 94 and likewise. The next thing which we are doing is y square. So minus 12 multiplied by minus 12, 144, minus 10 multiplied by minus 10, 100. Similarly for x, so for x1 we do the square. X1, see this value is 9, so 9 multiplied by 9, 81, 3 multiplied by 3, 9. The same thing we do for x2. When we do for x2, say we have this value 16 multiplied in the row of x2, 16 multiplied by 16 we have 256 and likewise we do the entire calculation. Then we multiply small yi. We have this small yi with small xi. We multiply these two, we get this thing. Next time we multiply small yi, each term of this with x2. Then we get x2. Then in the last term, what we do, we multiply x1 with x2. So we get this term. X1 and x2, this term, we get this term. Likewise, we do the calculation of it. Now, the sum of summation y square is 2536, summation of x square is 194, x1 square is 194, x2 square is 54,520. The sum of yi x1 is 318, the sum of yi x2 is 5380, the sum of x1i x20 is 3240. We have all these sums. Now, we need the summation of x1 yi. Here it is. We write it over here. We need the summation of x2 square minus. We need the summation of x2 iyi. X2 iyi. No, not this one. X2 iyi. This one. Then we need the summation of x1 i2 x2 I. In the denominator, we have x1 square. X1 square. We have x2 square. We have x1 x2 square. So we add, the numerator is this much, the denominator is this. The value of B1 is equal to minus 1.18. So we have got the values of B1. It is a bit more complicated than in a bivariate case, but nevertheless. Next time, for B2, x21 y1 means we take this value. For this, it is 194. We take this value. For x1 y1, we get this value. For this one, we get this value. Similarly, for the denominator, x1 square, again 194, and then this one, the next one is x2 square. We take the value of x2 square and then we calculate this. Finally, we insert all the values and we get 0.16. So the process is the same like your first one. Then the formula for beta naught. The formula for beta naught is similar, is y bar minus beta 1 hat x1 bar minus beta 2 hat x2. So y bar is equal to minus 20. Now here we have to do beta 1, we have just now calculated minus 1.18 multiplied by x1 bar. X1 bar is equal to 13. Now beta 2 we have just now calculated 0.16 and x2 bar 144. So we get the value of beta naught. Similarly, we have earlier defined seen what is the formula for r square. This is the formula for r square. Beta 1, we have just now derived beta 1, we put the value of beta 1, and y xi, this value from here we get. And for beta 2 we know it is 6, and then yi x2i over here we get the value over here. Beneath it is summation y square. Summation y square is over here. From y square, when we do the summation, we get 536. The r square is equal to 0.99. Adjusted r square, this was the formula for adjusted r square. We insert 1 minus r square value is this, we insert over here, then it is n minus 1. How many n? 1, 2, 3, 4, 5, 5 minus 1 is 4, and it is n minus k. There are k is equal to 3, n is equal to 5. So 5 minus 3, that is equal to 2. So we get adjusted r square value as 0.98. See, adjusted r square value is less than the r square value. So likewise, we can calculate the values of beta naught hat and r square and adjusted r square. To proceed further, what we do the calculation of summation e square is nothing but summation y square, small y square, e is also the small e, summation small e square is equal to summation small y square multiplied by 1 minus r square. Now, we have seen that summation y square is 536, r square is equal to 0.99. So we do 1 minus 0.99, so this is equal to 2.74. Then sigma square u was also used earlier. Sigma square u is equal to summation e square divided by n minus k. So e square we have just now calculated, 2.74 divided by n is 5 and k is equal to 3, so that is 2. If we do this, the calculation, we get the value of sigma u square hat is equal to 1.37. Now we want to find the variance of beta 1. Variance of beta 1, we have this formula, that is sigma hat square multiplied by summation x square divided by summation x2 square divided by summation x1 square x2 square minus x1 x2 the whole square. So we have just not found this value 1.37. These values we can get it from our table which we had done earlier. So we get this value and this. So finally, upon doing all the multiplication, we will find the variance of beta 1 hat is equal to 0.94. Now we need to calculate the standard error of beta 1 hat. So this is nothing but the under root of the variance. So when we take the under root, this is equal to 0.9723. इसको खत्म करने में 5 मिनट. अच्छा, तो दूसरा वाला मैं कल कर सकता हूँ. ठीक है, अर्ली मॉर्निंग क्लास है, फिर मीटिंग है, मसला ये है. हाँ ठीक है, मुझे 5 मिनट और दीजिए. So what we have seen, we have done the calculation of beta 1 hat which is equal to minus 1.18. We have done the calculation of standard error of beta hat is equal to 0.97. Now the t asterisk is equal to beta hat. For beta 1 we are doing beta 1 and the standard error of beta 1. So this is equal to this value divided by this value. This is equal to 1.2173. We are doing all this calculation in order to do the significance testing of the variable beta 1. My t calculated is equal to 1.21. We go to the t distribution. We are assuming a value of 2. Rule of thumb is for the value will be plus 2 and minus 2 over here. Now my t asterisk or the t calculated value is falling in middle of it. If it is falling over here, we accept the null hypothesis. The null hypothesis is your beta 1 hat is not significant, or here it will be say your beta is equal to 0, and alternate is beta is not equal to 0. If this is true, then it is my beta is not significant. Now what is happening, if you see, our t asterisk is falling in this acceptance region. In this region we accept the null hypothesis. The moment we accept the null hypothesis, we can say that this variable beta, or this is basically variable beta 1, this is not significant. So we have in today's lecture we have done the calculations of we have seen through the calculations, the numerical calculations of beta naught hat, beta 1 hat, beta 2 hat, and then we have seen how to calculate R square, we have seen how to calculate adjusted R square, then we have calculated the standard error of U and then the standard error of the coefficient, and then we have calculated the T asterisk. After calculating the T statistics, we came to the conclusion that whether my variable which is represented with the coefficient of beta hat, like here beta 1, is significant or not. So likewise we can do it for beta 2, and likewise we can do it for the any other. If it is if there is if there is a third independent variable, then we will have beta 3 also over there. So we can check for the significance of the individual coefficients over here. With this, I end my lecture. Hope it was clear to you. Thank you.